Welcome to corrosion. So corrosion is really just a redox reaction that we don't want to occur. So an example of an undesirable redox reaction is corrosion of metals. A metal here is attacked by a substance in the environment and converted to an unwanted compound. So if we have, say, a steel or iron-sided ship, and we have various salts in the water, as the steel corrodes, it rusts, basically. Right? This is a corrosion process. This is an unwanted redox reaction, where our iron in the steel is going from an oxidation state of 0 to a +2 or +3 oxidation state in iron oxide. So let's look here at the rusting of iron. So we've got the standard reduction potential of iron 2+ is less than the standard reduction potential of O2. This means iron can be oxidized by oxygen. And then at the cathode, we have O2 plus 4H plus 4 electrons react to give us 2 water molecules. And the standard reduction potential there is positive 1.23 volts. At the anode, we've got our iron solid oxidized to iron 2+ plus 2 electrons, and the standard reduction potential there is negative 0.44 volts. So dissolved oxygen in water usually causes the oxidation of iron, and our iron 2+ that's initially formed can be further oxidized to iron 3+, which forms the rust, the Fe2O3, with some hydrate involved. Oxidation occurs at the site with the greatest concentration of O2. So wherever that happens to be, it'll usually, at least on a ship, be close to the surface, because that's where the O2 is coming from the air. Other factors to consider include the pH, presence of any salts, stress on the iron, and contact with other metals. So things like presence of other salts. So salt water is significantly more corrosive than fresh water is, and you'll often see in coastal areas that salt through wave action, as the waves crash on the beach, some of those salts go up into the air and it will corrode metals around for miles, or speed the corrosion compared to similar metal in the open on the interior of a continent that isn't near a body of salt water. Corrosion can be prevented by coating the iron with paint or another metal, and this is preventing the oxygen and water from reacting at the surface of the iron. They're simply not getting to the surface of the iron. So galvanized iron is coated with a thin layer of zinc. Zinc does not react as readily as the iron will. The zinc is protecting the iron, and here the zinc is the anode and iron is the cathode. So we've got zinc 2+ plus 2 electrons goes to zinc solid with a standard reduction potential of negative 0.76 volts. The iron is being reduced from iron 2+ to iron 0 with a standard reduction potential of negative 0.44 volts. And this means that the overall cell potential here is positive 0.32 volts. The standard reduction potentials indicate then that the zinc is easier to oxidize than the iron is, and this is called cathodic protection. So the sacrificial anode of the zinc is destroyed. So basically, if we slap some zinc on the side of our ship, of our iron ship, then the zinc will get oxidized before the iron will, provided that electrons can flow between the iron of the ship and the zinc of our sacrificial anode. And basically the zinc gets oxidized and reacts with the oxygen before the iron will. And of course we have to replace our sacrificial anodes. This is why it's a sacrificial. They're being sacrificed. The zinc over time dissolves into this ocean, and we have to replace it. And so we do this on things like bridges, on things like ships, any sort of place where we have iron, especially in contact with seawater. We put zinc bars, and the zinc bars have to be replaced as they corrode over time. So that was corrosion.